Mhm. Okay. Do you prefer I share the screen as well?
Well, you sent the PDF, so it's not really necessary.
Mm-hmm. Because when I share the screen, in the end, the video recording is less better. No. Because it records mostly the presentation, not what is happening in the room. So, okay, next lecture. Yes, so today we will speak about two things. First would be a special algorithm, phase estimation, and this would be hard and abstract to see, but it lies in a kernel of a lot of stuff. Yes. And the second would be I give some insight inside the Shor algorithm, so the integer factoring, yes, and it would exactly uses phase estimation. Yes, so this would be a long lecture, yes, so please be prepared, I guess, and I expect that phase estimation could look too abstract, so please ask questions if you do, but this is the essence of the algorithm, yes, because it has a, like we had before, input of quantum oracle, which is quite an abstract input. Here the input would be even more abstract. So what is the goal? Let's assume that we have a unitary operator, so the operator which we can execute on quantum computer, so this operator U, and assume that we know certain eigenvector of this. Yes, because it's unitary operator, it has basis of eigenvectors. Yes, so there are a lot of them, and assume that we have eigenvector u. So such, in that case, it's eigenvalue. So it should be multiplied by u here. So it's not equal to the number, but to u. Uh, so then its eigenvalue necessarily have the absolute value 1 because the operator is unique. So it has the form e to the power 2 pi I times pi. Yes, we will call, it's often called, phi is phase of the state u. Yeah, so this, I mean, it comes both from physics. I like it from ergodic theory of dynamical systems, where such operators and such and the spectrum appears as well. Yes, so it is infinite dimensional. So here we use the pleasure of the fact that we are finite dimensional, so we really have eigenvectors and eigenvalues. Yes, so we have five. And the goal of the algorithm, yes, would be to find pi. And to find would mean that, okay, you will have certain qubits, you will measure them, and you will get pi as a result. Yes, like more formally speaking, so that you will find certain qubits, and after measurement of them, you will get phi1, phi2, phi3. Yes, so there would be several qubits, and this means that if you write it real number, real in binary representation, so 0 dot phi1, phi2, phi3, that would be close to pi. Yes, because of course, if pi is not something over power of 2, yes, you're never able to find exact value. Yes, so that's what is happening here. Yes, and uh, it would be a question what means we have u. Yes, because it's not means that we can just execute it here. So it would be a challenge for us because what we will need that for any k, we would be able to execute controlled u2 to the power k. Yes, so controlled u, this you immediately can do if you can do u because you just add control to each operation. Yes, control u squared. Yes, you can think that you do 2 times control u. But then, so at some moment, actually it's more than this. Because if you say that, okay, you can do this controlled u2 to the power k is controlled u2 to the power k times, then this becomes very long, very time-consuming procedure. Yes? And the quantum computing is about doing something fast. Yes. So for the phase estimation, the fact how you are able to do this is out of the scope of this algorithm. So this is your business to do this for your particular problem. And for example, for Shor, and later I will use it in solving of linear equations, it would be implemented differently. Yeah, so with different ideas. But still you will be able somehow to implement this gate. Yes, and we have state U means that, okay, there is certain qubits which are in the state U. Yes, so this part is simple. Yes, this part is straightforward. Yes, so before I say how it works, yes, before I say how this thing works, this a general, more abstract term. So when we would run algorithm, so we would have two type of qubits. In one, there would be stored value u, and we actually would never touch it. We would never change it. Yes, it would always stay in state u, but during the algorithm. Yes, and another, sometimes it's called clock register. Yes, because this is exactly the qubits which we in the end would measure to get this phi0, phi1, phi2, like those values of phi1, phi2, phi3. Yes, so this is the what we would measure in the end, and this would be the part which we would touch, but we would never change. Yes, so this is on a very, very high level. Yes, how it is done. Yes, so before I come uh, to the algorithm itself, yes, I would like to show some sub-part of it, yes, in a more details. Assume that I have not t qubits, yes, but I have just one qubit. And I put it into superposition of 0 and 1 and apply controlled u2 to the power j. What I will get? Let us just do a calculation. Yes, so we started with 0u. After Adamar gate, we have half sum of 0 and 1 u. We open brackets. Yes, so that's, and now interesting part. Yes, so we applying controlled u2 to the power j. Yes, so we applied what we get. So this is the first part. It stays unchanged because control was not executed. So in the second part, the first qubit is not touched, and the second is u2 to the power j. But now let us look onto this part, how it acts on a vector u. Because u was an eigenvector, yes, then we would just have a certain coefficient, yes, and this is the value of this coefficient, so 2 pi I phi times 2 to the power j, yes, times u. And now what I do, I just realize that, okay, I still have times u everywhere. Yes, so that's, then I keep it in a direct product state. So this scheme, because u was eigenvector, stays in a direct product state. So it's not the case that this scheme always keep direct product state as a direct product state. It keeps it only because u was an eigenstate. Yes, and okay, so it keeps an iterative process. So I could interpret that this scheme only changes this qubit. Yes, so, and I would do this on it. And doesn't touch the bottom line. And this I will use in a full scheme. So assume for a second that our value phi yes, was exactly, how to say, 0.5152 pi t. So this was exactly, yes, like this. What would be a result of such scheme as I draw here? Just let us look on it. So I basically take all the qubits which in uh, clock register, apply Adamar to each of them, and after this I apply controlled u to some power with respect to this qubit. Yes, to one of them u to the power 2 to the power 0, and another u to the power 2 to the power 1, and so on. And this is the same as I just implemented the previous scheme, but for this qubit with value, this 0 power, with this qubit, with first power, yes, so it's kind of consists of the scheme from the previous slide. In that case, I don't need to make, and I told that I interpret this that I don't touch, don't change the lower one and change only this qubit. Yes, so then I change those values of qubits independently. Yes, so I can write a direct product state and I can immediately do this. Yes, and okay, I wrote. Yes. And now I would like to use the fact that I have this form of yes. Then because I can write what is 2 to the power t minus 1 pi. Yes, it would be something integer and in the end pi t. Integer part doesn't matter, yes, because e to the power 2 pi I is equal to 1. So then I can, first term I can rewrite like this. The second term, 2 digits would be important, and so on in the last term, all digits. Yes, and let us look onto this state. Let us look onto this state. And the feature is that in the course, we already have seen such a state. Question where? So we have seen exactly this. Might be, except that T was named by another letter. Yes, we saw exactly this expression, which is helpful, yes, to understand what to do with next. Do you remember where? Okay, try to use deduction scheme. Try to be a Sherlock Holmes. Yes, we didn't have so many algorithms. Yes, so which algorithms we have? Deutsche Jodza we have. Okay, quantum oracle. Yes, Deutsche Jodza. The previous one, Grover. So quantum search. We have QRAM and quantum Fourier transform. Yes, chronologically we have quantum oracle and Deutsche Jodza. We have okay, we have multiple controlled operations. We have QRAM. We have quantum Fourier transform, and we have quantum search. Yes, to each of them there is a chance that it is, if you compare to the list. Yes, that's, I mean, this is the only to what it could looks like. Yes, actually, because multiple control was a bit play with ancilla qubit and control nodes. Yes, not here. Yes, quantum search was a different story. Was something rotating. Yes, was more geometrical. So I didn't write multiple qubit expressions. Yes, Kuram. Yes, potentially could be Kuram, but I mean that's okay. It doesn't. Yes. So it's quantum Fourier transform, and in fact, this expression is exactly quantum Fourier transform of poor state V1, V2, Vt. Yes. So that this was the way how we were proving that quantum Fourier transform works correctly. So we have found that this is the scheme, and this is the value of it, and we show that our scheme would have the same output. Yes. So this means that if after this I apply inverse of quantum Fourier transform, and if we do quantum Fourier transform, we can do inverse of quantum Fourier transform, I will get what we need. Yes, and this would be exact. Yes, so if U was without error, if we executed everything everywhere without error, we will get just exactly state T1, T2, T3, and so the measurement would be deterministic. Yes, and we will get exactly the value of pi. Yes. Yes. A little more. So this scheme is quite long. Yes. I will use sometimes in the lecture, yes, alternative notation. So it's here, please just consider this as a notation. Yes, not as a definition or something. Yes, so the idea here is the following. So when I use the line crossed, this would mean that there are several qubits there, yes, not just one. If I put here H, this means that I applied everywhere H. And there is a feature G. There is a letter G, which I wrote here. This is already specific for this particular situation. Yes, because after I applied everywhere Adama, I made a superposition of all the integers from 0 to 2 to the power t, yes, with the same weight. Yes, so kind of this is the sum of j. Yes, and each particular value j, I can specify. Yes, and here I put control to u to the power j, meaning that, okay, if those qubits are equal to j, I implement u to the power j to the bottom qubit. Yes, kind of this is the philosophical part. And this is exactly what is happening here. Yes, because for every j you have a binary representation of it, here 0 and 1s. And if at some position it is 1 that you apply u to this power, so if you look what exactly you apply to u, you apply to u to the power j. Yes? So because of this notation is used. Yes? And it gives kind of a correct impression of what is going on. Yes? And even here, I don't use that u is an eigenvector of capital U. Yes? Because it's just that, okay, I create a superposition. Yes, might be write it on a blackboard. Yes, I created a superposition. So there was a sum of, okay, 1 over 2 to the power t to the power 2, j, u to the power j, u. Yes, I created such a superposition. And by the way, it's quite an interesting idea, yes, because here j is inside the state, and here j is inside the coefficient. So I kind of mixed up the coefficient and the state. Yes, so this is mathematically nice expression. Might be we can play with it around, and we would. Yes, but do this. Yes, so this is a notation which I'm using. So today I will use it just once more. Yes, but later more times. So what is happening if phi cannot be represented in such form? Yeah, so pi is not some integer divided by power of 2. Well, this is a possible situation. Yes, and in that case, there is no chance, whatever computer we have, to get exact value of phi. Yes, because after measurements, we still can have only values which are integers divided by power of 2. Yes, so this is a typical restriction of computer. Yes, so in classical computer we also have this problem. There is no way to find exact value which is not in this form. In that case, there is a correct question which we should ask ourselves. And this question is the following. So we have a given n and given epsilon, and n should be considered as a large number, and epsilon should be considered as a small number. Yes, and we want to construct an algorithm which with probability at least 1 minus epsilon will give us phi with precision 2 to the power minus n. So kind of we want to get the result with arbitrary high probability, with arbitrary high precision. And of course, for each you make n bigger or epsilon smaller, you would have a price. Yes, for this. And the answer for this is the following. We just use the same scheme, yeah, and this large enough team, yes, and it works. Yes, so it would provide the result in this form. And on the next slide, that's exactly the expression for this team. It is a mathematical theorem which involves quite a lot of computations, yes, because, I mean, ideologically, it works the same as it was before, yes, because we just use that all operators are unitary, so if you have phi very close to 2 to the power minus, like to some value which is close to it, then I mean the operator would be approximately the same. Yes, so that's but you need to estimate all of this. And I don't think that this is a proper, place to give these calculations inside. Because in any case, yes, so here is the formula. First of all, it's not very hard. It's just n, yes, which is here, plus certain expression of epsilon, basically, yes. And if you put n to infinity, you will get t infinity. If you put epsilon 0, you will get here also infinity. So always would be in the balance. And moreover, this formula, I mean, I don't believe that this is exactly super important by itself. Yeah, so just idea, so if t is large enough, it would work. Yes, and it fits the philosophical idea that small perturbation inside quantum computing. Yes. Another story is that much more often the algorithm would be used not in a situation when you have a second register as an eigenstate, because it's very difficult to know eigenstate. So if you know eigenstate of an operator or all eigenstates of an operator, you potentially kind of know everything about it. All of it. Like mathematically, it's very hard story that you know the eigenvector but don't know the eigenvalue. But assume that you have a register psi. We know that operator U is unitary, so it has a basis of eigenstates. So we can represent this in such form. Yes, sum of coefficient times eigenstate. And the eigenstate has its eigenvalue. Eigenstate corresponding eigenvalue. And then now we remember that the phase estimation, but now I don't put measurement in the end. Yeah, so I on purpose forgot to include measurement here. I just run the same scheme. And remember, because in the end it is a linear operator. So if it was a linear combination, here we will get a linear combination of the result. Yes, so the resulting state phi would be a linear combination of those phases of eigenvectors. Yes, and this is the the idea. Yes, so that kind of this keeps a certain information about all the eigenvalues. And this would be extremely used kind of, it's not in a so extreme way is used in Shor algorithm, but in an extreme way it would be used in solution of linear questions. Yes, so kind of, yes, I presented phase estimation as an algorithm acting on the eigenstate, but it can be used for not eigenstates as well. But I mean, in that case, it's not very clear what is the outcome, what is my statement, yes? Because of course, if gamma k is not integer divided by 2 to the power, 2 to some power, then I mean, it's not exact, yes? So it's just, it's more in the sense that it has some information about, yes? So we would need to uncover this in the algorithm which we are using. Yes, so that's it, and this is the summary. Yes, so what we did, so we created such a scheme. Yes, we created such a scheme, and the scheme has the property so that if the eigenstate is have eigenvalue which is exactly integer 2 to the power t, it would give x here. Yes, it would create exactly value 5, exactly the phase. So if it is not, then if we consider large enough t, then we can approximate the correct answer with high probability. And if we have a state which is not an eigenstate, but certain linear combination of them, then in the end we will get on the clock register a certain linear combination of eigenvalues corresponding to station of this state. And this is it what I wanted to say about phase estimation. After this there would be a Shor algorithm. So I think it's very good time to ask questions. I'm pretty sure you were confused at some moment. It's too abstract algorithm. What? So gamma is a real number, yes, and I consider here UK as a basis of eigenvectors of operator U, yes, which always exists because it's a unitary operator, yes, and here I consider its phase, yes. So that's I consider, so this is an eigenvalue. Eigenvalue has absolute value 1. Yes, and I consider phase of this eigenvalue. Yes, and when I write gamma here, this is number between 0 and 1. And when I write gamma here, yes, it should not be, it should be integer here. Yes, but I write, as much as I can, yes, as long as I can, binary representation of gamma. Yes? And this is a play game. Yes, so that's here I kind of convert real numbers to integers. Yes, I convert it via multiplication. Yes, so gamma k was an integer, gamma k was a real number. Yes, and when I write gamma k, yes, this is I mean, yes, that I write 2 to the power t times gamma k, kind of its integer part. Yes. So I think this is because this is a real number. Yes, and gamma k is equal to 0, p1, p2, pt, and d. Yes. But what I actually write here, yes, I write here p1, p2, PT. So I have to cut at some moment. Yes. And if I have here not empty ending, then I would not get this with on certeza. Yes, I will not get it for sure. Yes, I will get it just with high probability. Yes, and those two values coincide. Yes, and okay, but I write usually like this. Yes, of course it could be strange to see an integer, a real number inside the state. Yes, but yes, this abuse of notation. But I will do this abuse of notation. Yes, thank you. It's actually a good remark because yes, I think it's the first time when I hear not integer but a real number. Thank you. More questions? Might be from Zoom. Okay, so let's then go to the second part, a Shor algorithm or integer function. So this is not the best algorithm to be present. Yes, but I still do, and I'm pretty sure that most of the courses does. Yes, and the reason is that actually quantum computers become famous because of this algorithm. They go out of the scientific community to the public because existence of this algorithm. And this algorithm is really very good because it has the following features. It solves a concrete problem. Yes, so it's not just abstract, phase estimation. Yes, which well, why do you need it? Yes, it has a certain concrete problem. Yes, and if you solve it, it also has a implications in our world. Yes, so it's would make difficult secure communication or create challenges to cryptography. Yes, but don't worry. Yes, so here, because if you create a quantum computer which can execute Shor algorithm, there would appear another cryptography algorithm. Yes, so of course it would be a big challenge because we have now everywhere. Yes, and to change algorithms everywhere. Yes, that's how many ATMs, how many cash machines we have. Yes, all of them should be, I don't know, replaced or software should be updated. Yeah, so that would have some consequences, but it would be resolvable. Another thing is that it is a complete algorithm. And so this is not like I have an assumption. There is an operator or there is an oracle. Yeah, so it just, I mean, you kind of, you get a number as an input and you get numbers as an output. And this is, by the way, a very good story. Yes. So that's now quantum computers are not very precise. Yes. So like I had this Quran. Yes. And kind of you can upload numbers there. Yes, but they would be always upload with low precision. So in this case, because what is integer factor of a number and we want to represent it as a product of two other numbers. Yes, it has a small input, yes, just one number, and small output, the two numbers or just also one number, yes, because divide you can on a classical. Yes, so it's a small input, small output approach. So this means that there is a potential chance that somehow it would ignore the existence of noise. Yes, so this is the feature. Yes, and why in that case, so this was a super positive introduction of the algorithm, why I don't give it in the full details in the course. And the reason is that because it's a combination of quantum part and the classical part. And classical part uses non-trivial mathematics. And so it uses some theorems from number theory, which I mean, even to formulate it would take quite a long time, yes. So that's because of this, I would present algorithm on the following strategy. So I will present quantum part, quantum kernel of the algorithm, and after this, I would say, please trust me. The classical part would lead you to a correct answer. Yes, so that I'm sorry. Yes, basically but that's what I have to do in another case. I also promise that the course will not use much more than linear algebra. Yes, and this is mathematically is much beyond the linear algebra. Yes, it's not cutting edge number theory, yes, but still it is beyond no, I think not beyond the master studies, but beyond bachelor number theory. So what is the problem which we try to solve? Yes, so we have a given integer number m, and the question which in general is set it up for integer factor is that to understand is it a prime number or it can be represented as a product of two other numbers, and if it can, then find those two numbers. So the feature with the algorithm, with the quantum algorithms are the following. So they are never, even if they are perfect, yes, they have a probabilistic nature. Yes, so they will almost never give you exact answers. Yes, it will give you with a high probability or something like this. So it's not possible to use quantum computer to say that m is a prime number. At least I don't know. Yes, but if you a priori know that m is a product of two numbers, it would help you to find which one of that. So kind of, you can think that with a high probability, it will give you some number, yes, which with high probability is divisor of n. Yes, so you can think about this in such form. Yes, so this is how it works. And if we speak about communication and not quantum communication, but secure communication, cryptography, yes, it is based, roughly speaking, on the numbers which are known, and they are known to be product to other numbers. Yes, so it's just help. Yes, and it would just give you with a high probability the good answer. Yes, so the quantum kernel is not an integer factor. We would solve with quantum computers different problem. And it is a job of people on a mathematical side to convert solution of this problem to construction of two integers, which are problem. Yes. So, and this is also non-trivial algorithm, but I mean, this is deterministic and this kind of I would explain what is the problem order finding. And if you can solve order finding fast, then you can construct decomposition by classical algorithm. And order finding is a different problem. So assume that you have integer number, the same m as was previously, and you have another integer which is co-prime with m. So the greatest common divisor is equal to 1. And if you got some x where greatest common divisor is not equal to 1, it is not equal, yes, then we can just take 1, the greatest common divisor, to numbers, and this is very quickly computed, yes, so by a Euclidean algorithm, yes, so that this is a fast story, and you find the M1 and you solve the problem. So how we will use this? Yes, we will actually pick up a random access, yes, and would do something with this random X and with high probability get good results. So what is the order of x? Let us consider a sequence. X squared modulus m, x cubed modulus m, x4 modulus m, and so on. Yes, then because this is infinite sequence and modulus m, there are just finite number of values, then there are two values which would be equal. Yes? And then I would divide by a smaller one. Yes, and I would say that x to some power is 1 mod m. Yes, and as soon as you get x squared, x cubed, and somewhere you get 1, then after this you will start to get x squared, x cubed. So this will be a periodic sequence with a certain period. Yes, and the order of x modulo m is the smallest, is the value r, which is the smallest such that x to the power r is equal to 1. Yes, kind of it says what is the period of this sequence. Yes, and remember, if we speak about period, yes, we were speaking about quantum Fourier transform. We were saying that we can find period. Yes, so in a certain sense, what we will do in Shor algorithm, we would construct this sequence very quickly. Yes, and this you will do philosophically and practically, we'll do phase estimation, and we will look for the period of this sequence. This is the part which I leave open, yes, in this lecture, that, okay, if we can solve this problem quickly, then we can find the decomposition of m to numbers quickly. This is, I mean, I don't know what to comment. Yes, so because it comes to non-trivial number theory, yes. And so in this lecture, I would consider only this problem. So it's also an interesting mathematical problem. Of course, if you present it in such form, yes, it would not become famous outside the mathematical or computer science community. Yes. So in order to make it publicly interesting, yes, you need to come to a problem which is really used. Yes, so which is this one. Yes, and but the quantum kernel is here. And let me see how it works, the quantum kernel. So before I just an example, how to see this. Yes, so let me take m equal to 21 and the x equal to 5. Yes, what would be the sequence? Yes, I start with 5. The next one is 5 times 5, which is 4. The next one is 4 times 5, which is 20. And 20 is kind of minus 1. Yes, so that's easy. So you go 20, so minus 1 times 5, you get minus 5. So 16. Yes, and minus 5, so minus 25. So which would be 17. Yes, so that's whatever. Yes, and so it's minus 4. Yes, and 17 times 5 is 1. Yes, so that's 6, and the order is 6. And you have 5, 4, 20, 16, 17, 1. And next 5, 4, 6, and 17, 1, and so on. Yes, so here the order is 6. Yes, so kind of what you will do that by the pair 21 and 5, so you have a given pair 21 and 5, and you want to get the value x as an out, value 6 as an out. This is basically what we do. Unfortunately, the life would be harder. We will not just, measure something and get 6 there. Yes. The life would be harder. So let us start explanation of the algorithm. Yes, so let us consider our number m. And consider two powers of 2 between which it lies. Yes, so m is between two powers, between 2 to the power l minus 1 and 2 to the power l. And I write less or equal to be mathematically correct, but of course this is a joke. So if m is equal to 2 to the power l, yes, we can easily decompose it. Yes, it's not a big deal. Yes. So, and now I would introduce an operator u, which would be the central operator of this part of the lecture. So I define it how it works on a basis states. So I have a basis state y consisting of L qubits. L is the number which is here. And it would work the following. So if y is less than m, then I multiply by x. So that the number which is from the input, then consider the value mod m. Yes. So this is what I have. Yes. And if the input was larger than m, then I just don't touch it. Yes. Important thing that because x was co-prime with m, this would be a permutation of basis states. Yes. First of all, it maps basis state to a basis state by the definition. And the second thing that every basis state would be achieved as a result. Yes, because x is co-prime with m. Yes, so you can divide by x modulo m as well. And so it makes a permutation of basis states. So this is a unitary operator. So it's theoretically possible to implement it on quantum computer. And because this is a reversible theoretical mathematical, from the classical computer world, yes, we could implement it on quantum computer, potentially with more qubits, yes, potentially with certain ancilla qubits. Yes, but you can reduce it to a complicated schemes of control not. And I would not explain how exactly. Yes. So a long story. Yes, multiplication is a hard procedure. Yes, to implement it into assembler on a level of bits. Yes, but this scheme exists. It's important that there should be some scheme which implements this, and it should be not a long scheme. Yes. And now I would like to use phase estimation. And to use phase estimation, I need to have certain eigenstates. And now I show some eigenstates, not all, yes, which are important for me. Assume that I know what is the order of x for a second. So this is exactly what we are looking for. We are looking for number f. Yes, but assume that we already know. And let us consider the state in a such form, the such state. So this would be sum of x to the power k mod m. Yes, so I consider those parts which are different. Yes, but with a certain coefficients. And the coefficient I wrote here, this will be exponent of 2 pi I sk over r. Yes, and remember, yes, at some moment, yes, it's even on the blackboard. Yes, it appears such expression. Yes, it's not exactly the same. Yes, because I put here x to the power k. Yes, not k itself. Yes. So, but now I have a form that basically I have here x to the power k. Yes, and here I have some number. Yes, e to the power minus 2 pi I s over r to the power k. Yes, so I have it in such form. Yes, and you can also ask me S about S. What is the value of S here? Yes, I have for different S, different US. Yes, so this is not just one state, it's for every S, I have my own state. Yes, and later we will see that this is an eigenstate, but of course this is, I would like to clearly state this, that such a quantum state exists, but there is no way we can construct it. Yes, but it doesn't forbid it to exist. Yes, so I cannot write a scheme which would make a quantum computer into this state. I don't know how. But still, in calculations, we are not forbidden to use it. Yes. And it happens that this state is an eigenstate. And this is a very easy story because what happens when you apply U to it? Yes, you only affect the right part. You only affect this part. And if you don't affect coefficients, you just will write here x to the power k plus 1, yes, because you don't have any operations here. Yes, you just multiply inside. And now it comes very easy because you can write here k plus 1 and write here k plus 1 and get certain element on front. Yeah, so this is just equality. Yeah, so and here I didn't change, and here I basically multiplied to this exponent divided by. And now it comes the fact that I use the fact that R was the order of M, because the set of those guys here, the set of states here and the set of states here is the same. Yes, but because what it was. Yes, let me draw a picture. Yes. So there was x squared. So I started from 0. Yes, so it is 1 x squared x cubed x to the power r minus 1, and after this 1 again. Yes, and the sum which I wrote here, us, is the sum of those states with a certain coefficient. Yes, and the sum which I have here is the sum of those states with a certain coefficients. And the set of them is the same. Yes, and now what is happening? Yes, so because still, all xk are different, by the value x to the power, you can determine the coefficient in front of it. It doesn't matter, yes, because you consider to which power was x, and you have this exponent. Yes, and this one, what is the difference, is the same in all elements. Yes, so it's just become equal to e to the power 2 pi I s over r of us. Yes, and you can put this guy out here. Yes, and after this is those two states just coincide because they have the same basis state involved with the same coefficient. Because if you write here k plus 1, you need to write k plus 1 here as well. And because R is the order, then when you go across the R, yes, when the last element becomes the first one, yes, so it becomes the same. Yes, so kind of I removed one, I added one. Yes, so this is an eigenstate. Oof. it seems that we did a great job. Yes, so potentially we would create state US. I never would be able to do this. Yes, then if at this moment we applied phase estimation to it, we will get S over R. Yes, and if we use S, then we can recover R. Yes, from this, and like okay, if we didn't know S, then still it would be a lot of information about what is R. Yes, that's. I mean, if you get 0.33, might be R was. So if your result of your measurement is 0.33, might be R was equal to 3. Yes, in this philosophical sense, it's enough information. It would be enough information. But the problem now, there are two problems, actually. The problem one is that we cannot construct US. Yes, and we need somehow to resolve it. So we would like to apply phase estimation to it, yes, and get what we want. Yes, for example, we would like to apply to U1, yes, get 1 over R. Yes, and this is the answer, yes. But we could not do this. And the solution to the problem one would be quantum. And I would explain. Yes, so it would lie in quantum philosophy. There is a problem two, that I told that I would apply phase estimation. Yes, and to apply phase estimation, I need to have an efficient way to execute controlled U to the power J. Yes, and I need to do this efficient. Yes, because I want to do the end fast. Yes, so then I need to do this kind of fast as well. And for this, there would be classical algorithms. Yes, so that's actually U was this classical operator. Yes, it would just was basically sending Y to X Y, yeah, mod M. Yes, and there is a good, it's just multiplication. It happens that also you can make a classical algorithm which would do like this quickly. Yes, it would be method of a classical world, not method of quantum. But I will tell also how to do this as well. Yes, so okay, how we will solve problem one. Okay, we know this US, but there is a wonderful identity, yes, which connects different values of US. It happens that we don't know US by itself, but we know their sum. Yes, and the reason is that okay, look, yes, all US, yes, was based had coefficients in front of the same X case. Yes, the same basis states. Yes, so kind of there is a chance that we can properly summate them in order to have a lot of cancellations. And the answer is yes, we just need to summate them. Yes, and then we get a good result. And okay, here the calculations are completely straightforward. We just, okay, let us look onto the sum. Yes, here it is. And okay, we need to substitute the value of US. Yes, here and okay, 1 over square root of R times 1 over square root of R is 1 over R. And after this, we have a double sum. And okay, after this, we have double sums. The first idea which you should have is just to flip the order of summation. And if you flip the order of summation, then you get on top k, and so x to the power k becomes the same for the rest. Yeah, so here becomes a sum of real numbers. Yes, and this is sum of exponents, and if you look carefully, yes, you will see that this is a geometric series. Yeah, so this is because if k is fixed, you just this is an arithmetic progression, yes, and this is an exponent of arithmetic progression. And okay, if it is a geometric series, then we can find the sum. And it happens that if k is not equal to 0, yeah, so when this is exactly the geometric series, not a constant, yes, then the sum is equal to 0, as we often saw before in the course as well. Yes, so it's 0. And if k is equal to 0, then the sum is the number of elements in the sum, because all of them are 1. Yes, so it's R, and in the end, this is just 1. And of course, state 1 we can easily construct. Yes, we just need to put one not operation. Yes, so this is wonderful. And okay, but this is just an identity. This is not a result yet. Yeah, so we have those two properties, that each US is an eigenstate. Yes, and their sum is equal to 1. What would happen if we applied phase estimation to 1? Yes, it would be the same if we apply phase estimation to some of those elements. And phase estimation is a linear object. Yeah, so this would be sum of phase estimations of each US. And now it comes, not a good part of me. Yes, because quite often, normally R is not power of 2. Yeah, so S over R would not be some constant, some integer divided by power of 2. So phase estimation would not give exactly S over R. So I will write it like this. And I would not much specify this lecture what exactly does this mean. Yes. So we have a sum of this. And now if we, after application of phase estimation, we measure everything, we will get value S over R. Yes, with a randomly distributed S, so we do not have any control on S. And this is good, but not bad. Yes, because potentially you can have S equal to 0. So potentially you can get 0. Yes, and if you get 0, then you don't know nothing about R. Yes, potentially R can be not a prime number, but something else, and then you will get S over R, not the way you would not be able to recover R. So this is already also part from classical algorithm, classical world. In fact, that if you find enough samples of this, so you will find enough values of S over R, yes, then you can find R. Yes, in the easiest case, you kind of write, in the easiest case, you will get two values, S1 over R and S2 over R, yes, and if greatest common divisor of S1 and S2 is equal to 1, yes, then you can apply kind of Euclidean algorithm and just get 1 over R as the combination of those two elements. Yes. Of course, the life is more hard because it might happen that you will get two values, but they are not coprime, yes, and so on. So there is a mathematical issue around this. But there is a way to do this, and so it's called actually continued functions, the way how people work with this. But this is also not quantum, it's number theory. Okay, now it becomes bachelor level number theory, but still, it's not the purpose of the course. Yes, so, and finally, yes, so let me see how the algorithm look like. So I took T qubits here, and after this I applied phase estimation part. So I applied, say, u to the power j here, and inverse of quantum Fourier transform. And before I put the initial state in 1, yeah, so I measure the end. So this gives me S over R. And important thing that I told that, okay, I need from values S over R, I would be able to recover R. There is a detail. Yes, I need to know S over R with high enough precision. So there would be a restriction that T has to be at least 2L plus 1 and plus some term determining the probability that everything will be good. And in that case, just the value which we would measure would have a quadratic size error. So that's with a high probability, the phi which we measure would satisfy this inequality. This is the important part. And I need classical details. So let us have a short break, and after this we quickly actually finish. We're very close to the end of the lecture. Let's have 5 minutes break. And by the way, questions are always welcome. Yes. Oops. By the way, you're welcome to ask questions on the parts which I quickly going through. Yes, so uh, by the way, yeah, so this is the scheme which we have. It's not so difficult scheme. Yeah, so that we put here other marks, yes, we put control u to the power 2 to the power g, and we put quantum Fourier transform. So this is uh, not so much, yes. One should understand that at the moment when it was invented, yes, so there was not known phase estimation, it was not known quantum Fourier transform, yes, so this was how to say. Later, people decomposed it in the quantum Fourier transform and phase estimation. So when it was invented, it was a bit strange, yes, because here you use this controlled u to the j, yes, and u operator is a classical operator, yes, so you kind of just transport algorithm from classical to quantum, yes, and so this part is completely classical. Yes, you have here just other marks, yes, but here you start to have very strange operations with the controlled ry rotation on some angles, yes, so that kind of up to here it was more or less classical, yes, and here it starts by some reason go to unclear world, yes, yes, okay, that's what not. Yes. So I explained problem 1. Yes. So what to do with the fact that these eigenstates we cannot construct. So we constructed the linear combination. But what to do with controlled u2 to the power j? Yes. In fact, for this you need two classical algorithms. One which would map x to x squared. And remember this is not reversible. Yes. So in any case, kind of you will have ancilla qubits here. Yes, but I omit. Yes. And the second thing, we will need not operator u, but we will need a slightly more difficult operator v. Yes, which would have as an input not just y, it would have z and y. Z it would not change, and to the second it would work either zy mod m or keep y untouched. And in that case, after proper combinations of this element and this one, yes, you will start substituting here x, and you will get u. Yes, so that's no, that's v over xy is equal to x uy. Yes. After this, v x squared y is equal to x squared u squared y. Yes, v x2 to the power k y, and you can do this, you can create this number with k operations. You do x squared, x squared, x squared. So k is a small number of operations, not exponent. Yes, is equal to x k u2 to the power k y. Yes, so you have this construction of u to the power k, and to add control, you just add control to every single operation. Yes. So this is a classical problem. So I never go here to the difficulty of quantum computer. There. Yes. And okay, period finding. Yes, so this is actually the last slide. And I wanted to come here. Yes, and I have this exposition here because basically what we did here, yes, we created a state like this. Yes, and u to the power j, yeah, assume for a second that it was applied not to 1, but I mean to no, oh, no. We create, no. Sorry. This I should erase. This is not correct. Yes, sorry. Yes. So we had this x to the power k, yes, which was a periodic sequence. Yes, and so on. And it's not very visible here, yes, but in fact, in a certain sense, related, we consider this as a, we created a sequence like this inside, yes, because kind of what we did, we were just multiplying by a certain value, yes, and after r iterations, it comes the same, yes, and if you look on the coefficients which are here, yes, in front, so kind of in the end we have a sum, yes, so after we did all what we did, yes, we have a sum of some coefficients k, yes, and in fact, philosophically speaking, those coefficients are almost periodic because whatever you, so assume that below, yes, is not state 1, yes, assume that it is state us, yes, then what we get, yes, so if it was state us, yes, we will get here sum of e to the power 2 pi I s over r times k. This is what we would have. Yes, as a coefficients here. And this is R periodic sequence. Yes, this is R periodic sequence. And okay, we don't know US, but for all US, it is R periodic sequence. So if we consider linear combination of them, this would be R periodic sequence. Yes, so in fact, what we did when we substitute one here, we didn't touch one, but we created on those clock register R periodic sequence. Yes, and okay, I demonstrated before that quantum Fourier transform uh, allows us to find the period. Yes, and this is a philosophical concept. Yes, so that's okay. Formally, I write phase estimation. We come to phases. Yes, but in fact, when this algorithm was created, yes, it was created in a way. Okay, this part creates a periodic sequence, and now quantum Fourier transform will find the period of this sequence. Yes, okay, much more smarter way, much more uh, quantitative. It's easier to quantitate, yes, because it's almost, yes, it's not that we get exactly the period, because period is not power 2, yes, that it's simpler to quantify, it's simpler to prove theorems when we speak in the language of phase estimation, yes, so it's simpler to get this estimate, yes, which is needed on the level of phase estimate rather than on a level we are looking for periods. Yes, but still it was philosophically looking for period. Yes, and you can set up a problem of finding period just naturally. Yes, and you can solve it via the similar schemes as well. Yes, so assume that we have a periodic function which get an integer and output is 0 or 1, yes, then if we have an oracle implementation, yes, then, then we can, by this scheme, we can find the period in the same sense as before. So you take several qubits, you apply Adama to them, so you create an equally uniform sum of elements. You apply Oracle, yes, and here it is just one qubit, and then you will get and apply inverse Fourier transform. So it's very similar to phase estimation scheme. Yes, it's not exactly, yes, and in fact you will get a good approximation S over R inside it for some S. Yes, the same way, because here it would be kind of a periodic sequence. Yes, and then so in fact to complete by classic story. Yes, because we have not 1 over R, but S over R. We would need still T to be the same, where now L refers to the number of digits in R. Yes, so before it was corresponding to M, yes, but here it would be corresponding to R. Yes, and so we get such estimate and blah, blah, blah. Okay, so that's it. Yes, I promised a long lecture, but not so long. Yes, but I think it was hard enough not to add anything to it. Yes, so please don't hesitate to ask questions. Yes, and as a summary, so I showed phase estimation. Yes, which might be the last slide. It's still the main thing which I presented today is the phase estimation, not the short. The short is just uh, an example, basically. Yes, but uh, the main thing is phase estimation because this is a major tool. Yes, So we have now we have actually several tools, yes, by which you could combine. Yes, yes, that we have Quran, yes, so we can upload data in quantum computer. We have quantum Fourier transform, which is mathematically good by itself. But by the way, up to now, we used it only to find in periods. Yes, everywhere. Yes, so that we didn't use it more. We have Grover or quantum search. Yes, and now we have one more element of the toolbox, phase estimation. Yeah, so basically, at some moment there was a, I think, I don't remember who, yes, but someone asked a question, do we really, write on the level of assembler? Yes, we were writing on assembler. But now we start to grow up, yes, because Kuramba itself, it's already not assembler level. Yes, I can imagine Kuram function in analog of Kuram function in Python. Yes, but yeah, I mean in the classical computation. Yes, I can imagine analog of QFT in Python. I mean, it's even exists. Yes, you have a discrete Python dot discrete Fourier transform. Yes, you have it. Okay, Grover is more hard story because we have Oracle here. Yes, so that, I mean, we have also search functions in classical computers. We give you, which gets as an input something like true or false. Well, is a callback true or false. Yes, I don't know what is the modern name. Lambda expression, callback, monads. Yes, no, because I learned software development before, yes, so it was kind of a callback. Now I see that the world has changed, yes, so and now we have a phase estimation, yes, as an element of our toolbox. And yes, as an element of toolbox, now we also have all classical computations with Atzilla. Yes, so we have a relatively large toolbox. Yes? And actually, the next two lectures I would devote to using this toolbox. Yes, kind of. I would at some moment I would need to go to assembler back, but only on a low level. Yes, I would try to create a solving of linear equation. And this is, by the way, how to say, not really solved problem right now. Yes, so it sense that people try to improve this algorithm as much as possible. Okay, before I do this, yes, so I left the space, yes, so I would need to add to two toolbox Hamiltonian simulation. Well, let me leave it as a part of linear equations. Yes, because I don't want to uncover right now what is Hamiltonian simulation. Okay, any further questions? If no, then that's it for today. Let's enjoy the sun. Oof.